Hello, I'm Scott Steinmetz, a student in the Perception and Action Lab at RPI. Today, I'll be discussing work we've done to test a method of organizing a component of the competitive dynamics model such that the cells tune themselves to the current visual environment without need for manual parameter selection. The competitive dynamics model is a computational neural model of optic flow processing that simulates areas of the early primate visual system. Throughout this walkthrough, I'll be using this video of an agent moving in 5 randomly chosen directions through a realistic neighborhood environment as the example stimuli, and showing various area activities related to it. Our model generates human-like heading estimates in the form of dorsal MST radial cell activity. Radial cells respond to expanding patterns of optic flow like those generated by self-motion in that direction. In this video, yellow regions indicate high activity of cells with receptive fields at those locations. And the true heading direction is the red reticule, while the blue X is the model heading estimate. If you want to watch any video again or would like to read detailed descriptions, please see the YouTube URL at the bottom right of the poster and in the presenter messages. As you might expect, models such as ours have many parameters which affect performance, and there is considerable study about what values to use. Today I'm presenting a principled method for extending an efficient sensory encoding approach to parameter selection so that speed cells are dynamically attuned to the current visual environment, which results in impressive performance gains over a static attunement. Here's the optic flow for our example video, which shows optic flow of many speeds from slow to fast. Speed cells in model area MT are sensitive to a specific range of optic flow magnitudes governed in the model by their tuning curves. Slow speed cells, like these ones, are most active when there is slow optic flow in their receptive field, in this case largely in locations that are distant from the agent. Conversely, fast speed cells respond to fast optic flow, like that from nearby portions of the environment. Determining the arrangement of speed cell tuning curves includes defining both their peak low locations and variances. Simoncelli and Ganguly described a method for defining tuning curves such that the information about a variable is ideally captured, given a probability distribution of that variable's values. They suggested that the distribution of values statistically found in the environment be used for the best outcome. We propose a dynamic attunement to recently seen values for that variable, in our model's case, optic flow. In this next video, optic flow will be on the left. The distribution of recently seen optic flow will be in the top right, and the bottom right will be the ideally chosen tuning curves for that distribution. And as you can see, even within a single environment, the distribution of optic flow varies widely. To evaluate the difference between a dynamic and static attunement, we generated 60 videos like our previous example across 2 environments, including this warehouse setting. Each video had 5 translations in random heading directions at random speeds and started at a random height above the ground for a natural sampling of widely varied optic flow. Let's start with a comparison between 1 dynamic condition and 2 static conditions. As a control, the first static condition was an attunement to a uniform distribution of optic flow values. For a classic static condition, the model was attuned to the environmental probability distribution of all optic flow pooled across all 60 videos, and in the dynamic condition, the model was attuned to the optic flow seen in the previous 10 frames. When we looked at this, we found that in the dynamic condition, the model's final heading estimate was significantly more accurate than either static condition. While the difference is a little over a single visual degree, that's a 20% improvement in accuracy. Further, the improvement was not just in the final estimate accuracy, but also in how quickly the model reached that estimate, or the latency of the model estimate. This graph shows the best fitting sigmoid curves for each condition, with dotted lines marking the frame the final estimate is reached for those curves. Both of these graphs show the heading error as normalized to how large the heading shift was, so whether the new heading was 70 degrees from the previous heading or only 10, the error starts at 1. The final graph controls for the performance of the static uniform, showing us more clearly what frames the dynamic condition has higher accuracy than the static attunement to the environmental optic flow distribution. We then examined whether the time horizon of the dynamic condition mattered, as in whether the model was attuned to the optic flow from the previous 1, 10, or 30 frames, and this had no major effect, though the 10-frame condition had some slight advantages, mostly due to numerical consistency. So, in conclusion, a dynamic efficient sensory encoding approach to speed cell tuning produced more accurate heading estimates more quickly than a static one. And what the time horizon of the dynamic tuning was didn't have much of an effect. But more broadly, this principled approach removes the need for manual selection of what distribution the model should be attuned to, and this could be applied to many variables encoded using the efficient sensory encoding approach. This further gives the payoff that it enables the model to adaptively adjust to new environments, motions, and situations automatically. There are more details in the video descriptions at this URL, and please ask any questions you might have on VSS or via email. Thank you.